Good afternoon and good morning, everyone. Welcome to this session. We have one invited talk in this session, and if you have any questions, you can raise your hand or just send your question in the chat box. So now let's invite the invited speaker, Dr. Mohammed Ashif Khan from Qatar University. Dr. Khan will speak on real-time crowd counting and the age. He's a senior member of IEEE, a member of IET, and a chartered engineering with the Engineering Council UK. Okay, now let's welcome.
Thank you very much, Sally. Let me share my slides first. Okay, so my full screen is visible?
Yes.
All right, so hello everyone, and thank you for being here for this session. I will first present my invited talk on this topic, as you can see on the screen. And I'm also chairing this session, so for the remaining sessions, I will be available and attending all these interesting sessions as well. So let's jump to the topic now. This topic is real-time crowd counting at the edge. And you know that crowd counting with computer vision, it's an interesting technique and interesting applications of computer vision and deep learning, which is used to provide the estimate or count the number of people, animals, or any kind of objects in an image or a video frame. So, like given this image on slide, you can see you need to estimate how many people are present in this image. Now, this particular technique in computer vision has many interesting applications in different scenarios. For example, you can use it to count the number of customers in a shopping mall, and it can have many applications in the retail sector. You can use crowd counting to count the number of pedestrians which are crossing on the road for transportation planning. You can count the number of spectators in a stadium for planning of the events. And you can count the number of protesters in a political rally, for example, for law enforcement agencies. It can be quite useful. You can also use crowd counting to count the number of animals in a forest or a farm for protecting wildlife in our forests. So, given these different applications, I mean, there could be more applications beyond that, but these few applications were just to motivate how crowd counting can be useful. Now, given these applications, let me start with some of give you an idea of how traditionally crowd counting was being implemented. So, traditional methods for crowd counting were all based on classical machine learning and which uses handcrafted features like detecting different shapes in in an image or body parts of the people or object of interest which you want to count in that image. Or sometimes, or some techniques uses global features like gradients or foreground segmentation to give you an estimate of the ground. However, all these traditional methods were less accurate in challenging scenes. Now, what are challenging scenes where these applications could potentially fail? So some of these challenges for crowd counting, which are also common in other computer vision applications like object detection, for example, as well. So some of these challenges are like single scene versus multiple scenes. So when you train a model, a deep learning or machine learning model on a single scene, as you can see on the left-hand side, the top picture, it's quite easy, for example, to count the number of people if the scene is the same and when you train the model and then you deploy on the same scene. But when the scene changes, for example, on the right-hand side on the top, it's become challenging to train a model on one particular scene and then deploy it to count the number of people in another scene. So the performance of the model could potentially downgrade. There are other challenges, for example, scale variation. So some objects in an image could potentially looks bigger than other objects, and this can also impact the accuracy of the model. There could be variations in crowd density, for example. Some part of the image could contain more number of people than other parts, or even in some image, all the crowds could be potentially located in one particular segment of the image. So this also is another challenge for crowd counting models. Yes, there could be occlusions, like some objects will be not fully visible, and it's difficult, excuse me, it becomes difficult for the crowd model to detect those partially visible objects. And sometimes, if the background of the image is too complex, it's again a challenging task for the crowd model to detect accurately or estimate accurately the number of objects. So, given these challenges, traditional methods using machine learning for crowd counting were abandoned. Like most of the today's method uses deep learning applications, and the de facto method for crowd counting today is density estimation, and it all uses deep learning. Now, what is density estimation and how does it work? If you see this image, whenever we implement crowd counting for density using density estimation method, we take the image and we take all some sample images or a data set of images which are all labeled with 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 the density with a dot map, for example. So for each object in the image, you have the position of every object. For example, if it is human crowd, as you can see on the slide on the in this image, let me open the pointer to, yeah. So for example, you see here for this image, you have different number of people, and you have to provide labels for this image to train the model. And the label in this particular application is you have the head positions of each person in this image. So the head position is represented by X and Y values. So these X and Y values for each head position provide the labels or the annotations. Now, to use these annotations in the training of the deep learning model, we convert it to get a kind of dot map. So we have a dot on each head position, XY value, for example, 10 and 100, we have a dot here. While all the remaining pixels in this dot map are zero values. However, it's not easy to train a deep learning model with such kind of sparse dot map. So we further convert this dot map by applying a Gaussian kernel to get a density map. So each dot here is spread out here in the density map, and now it becomes more easy for the deep learning model to get trained. Now, once you train the model with crowd images and its corresponding density maps, you get a predicted density map at the output of the image, and you can easily get the total count of the people by integrating all the pixel values in this density map. So once you get the density map, it becomes easy to get the total count. So here it's more clear, like how you get the dot map from the image, and then how you convert it to a density map. You can choose different values of the Gaussian parameter, the scale parameter. So the higher value you take for the scale parameter, you get a more spread. So it depends on the size of the object in the image. So, for example, if you have more people, the head sizes will potentially be smaller. So you can choose a smaller value of the scalar parameters, or if you can choose a higher value if required. Now, looking into a brief review of the history, like how crowd counting models were being proposed earlier and how this research moved on. So this picture shows a number of crowd counting models trained on two different data sets, Shanghai Tech Part B and World Expo 10. And starting from 2015 to 2012, sorry, 2022. These are the different models. If you look into this picture carefully, you will see a very important trend. For example, so the models showing on the left side, you see their performance gains were quite visible, quite, interesting. There were significant gains in the performance. However, when you move to the right-hand side, you see like the gains achieved by those models were very incremental, and it was not very significant, but still like they all bring up some innovation in the model architecture. But this was just to show you like many of these models in terms of performance were not very significant. Now, this was like how we do crowd counting applications, crowd counting modeling, and how different models were proposed. But there is another unique challenge when you implement or deploy crowd counting models on edge devices, for example, on drones, on cameras with small processors. These models actually, the crowd counting models, most of the time they use deep, front-end models. For example, most of these models uses VDD16 or ResNet or GoogleNet, and you can see the number of parameters on for these models, like they are in millions. And so their floating point operation will also be higher. So these edge devices, as I say, like cameras or drones, they are resource constrained. These models cannot, these models require a high computational power, while the edge devices may not have these resources. So what is the option then? The option is use shallow architectures, smaller architectures for crowd counting. But the problem with shallow architecture is that they cannot achieve that kind of high accuracy. So then there is a severe need that we should somehow improve the accuracy of the shallow models, right? So how to improve or enhance the accuracy of the shallow models for crowd counting applications? Now, there were different options. For example, one option is the first two options, as you can see here on this slide, model pruning and model quantization. So you take a deeper model, a deeper crowd counting model, and you prune it or quantize the model, and you know how pruning and quantization methods work. So somehow both of these methods reduces uh, the computational complexity of these models. So you can take a deeper model and somehow you compress this model into a representation which is computationally less expensive. But we're not going to discuss those techniques, pruning and quantization. Instead, we are focusing on these four different techniques in the red color: curriculum learning, importance sampling, knowledge distillation, and training on multimodal data. And while discussing these methods, I will give you a glimpse of our recent research contributions using these methods, that how we use these methods to train shallow architectures, shallow models for crowd counting, which are much suitable for for edge devices, especially in real-time setup where you cannot afford a higher inference delay and you want the inference time to be as low as possible. So starting with the curriculum learning. What is curriculum learning, by the way? Now, in traditional machine learning or traditional deep learning, you always have a training data set as represented by D here, and you have a model to train on. And usually you take a loss function, which you reduce over the training period. Uh, by this technique, right? So you train the model, you are actually reducing the loss function over this data set, which is represented here by xi, yi. Uh, so this is in traditional learning. So you what you do is you take the model and you fit it you take the data set and you fit it to the model in either all together, which is not all the time, especially if your data set is bigger. You give it in batches. But curriculum learning is a different technique than standard training. So in curriculum learning, we take the data set and we actually uh, sort all the data in the data set in order of increasing or decreasing complexity of each sample. So the notion behind curriculum learning is that humans actually, because most of the machine learning, they are inspired from humans, right? Or learning process in humans and animals. So the notion behind this curriculum learning is that humans normally, they tend to learn better if the task which they are learning are presented to them in a particular order of increasing complexity. So you give them a task, a simpler task first, they learn the simple task, and then you give it another more difficult task, and they will do it better in this way. So this is the same technique is being adopted in curriculum learning. So in curriculum learning, you actually break down the data set D into smaller subsets like D1, D2 up to DT, and before splitting this data set into subsets, you are actually doing it in terms of increasing complexity. So D1 has a lower complexity than D2, and D2 has a lower complexity than D3, and so on. So once you sort this data set into the complexity, order of increasing complexity, then you fit these separate subsamples to the model. And this is the representation here. This equation shows the curriculum learning equation. So now you have the data sets sorted in terms of complexity. Now, there are two important functions in curriculum learning. One is called scoring function, the other is called pacing function. So what is scoring function? When we say we have to arrange the data in terms of increasing complexity, how we define complexity? So to define complexity, we actually score or rank each sample in the data set. And there are different ways to do it, right? For example, you can use another deep learning model and just run all the samples through the deep learning model to find the loss or to find, let's say, the accuracy of each sample. So you will get to know like which sample is easier for the model. So by taking these loss values or accuracy of on each sample, you can get an estimate of the complexity or difficulty of each sample. So you use the scoring function to rank these samples in terms of increasing complexity. And then you choose a pacing function. So you have now, let's say, the sorted data set. Now, how to increase the complexity in each iteration, right? So you use a pacing function, and a pacing function is typically a monotonically increasing function. You can use different functions. For example, here you can see a step function, but you can also use other functions, for example, a log function or a square function or any other kind of monotonically increasing function. So this defines the pacing of the data set complexity. So how much you want to the complexity to be increased in each iteration of the data set. Now, using this notion of curriculum learning, we developed a lightweight model called, we named it LCDNet, so lightweight density estimation model for drone applications. And the idea for this was that shallow models can be perform much better if they are designed and trained well. So what do we mean by designed and trained well? Here you see the architecture of the LCDNet that we designed. So by saying designing well, I mean that we optimize this model specifically for drone applications. And as I said before, we need a kind of density map to train crowd counting models. Now, to get the density map, we need the blobs or the dots or the each head position, and the spread of the dot is very important. So how much should we spread each dot using the Gaussian filter? So what should be the scale parameters of the Gaussian filter really matters. So if we have a good estimate of that scale parameter, crowd counting models can perform much better. Now, what we did is we said that in drone applications, we have an intrinsic advantage. For example, a drone with a camera is looking at the crowd from a bird eye view, and all the objects which are visible in the frame will most probably will most probably be visible with equal size. For example, in normal CCTV cameras, if there is number of people in terms in front of the camera, the people which are closer to the camera will look bigger than the people which are far behind the camera, right? So, but on the contrary, in drone applications, all the people on the ground will potentially look of the same size for a drone camera. So we can have a fixed size of the scale parameters of the Gaussian filter. So we said that it is easy for the drone camera, to get the scale parameter by just taking its altitude, and we can take potentially a same size of the scale parameter. And when we have the scale parameter fixed, we can actually use a simpler model, a simpler or shallow architecture to learn it well. And to further enhance this learning of the crowd density, we employed the curriculum learning strategy that I explained in the previous slide. So we sorted these samples in terms of in batches in terms of increasing complexity, and then we fed it to the LCD-net architecture. And the LCD architecture here shown on the bottom of this image you see here, it's also very shallow, very lightweight. One of the techniques that we also borrowed from other, deep learning architecture for resource constrained devices, like this was particularly taken from the efficient net model, that we spread here the 32 by 32 filter, the 3 by 3 filters, which are actually 32 filters. And instead of taking 3 by 3 filters, what we did is we took 32 filters of 3 cross 1 and then 32 filters of 1 cross 3. So potentially, the number of filters increases and the complexity of the overall filters will be less than if we use 3 by 3, 32 filters. So this was some of the caveats that we used here by deploying and training the LCD-net model. Right. And then the next model is CLIP. So in CLIP, we use curriculum learning, but we enhance it with iterative pruning. And this is a data-centric approach. If you see here in this algorithm, what we did is actually curriculum learning can potentially enhance the model learning performance, as we saw in the LCD-net. And one way that we can further improve the performance is that when we take the curriculum learning and we score each sample, like we measure the difficulty or the complexity of each sample in curriculum learning, we can find out that there will be always some samples which will not be potentially contributing to the learning performance. I mean, their loss value will never reduce, right? So why to take those kind of samples which are not contributing to the learning? So in CLIP method, in this algorithm, excuse me, we are iteratively, in each iteration of the curriculum learning, we are pruning or we are eliminating those non-contributing samples. And when you reduce or eliminate those non-contributing samples, you can actually enhance the learning performance. Now, if you see here on the on this learning curve, you will see that in standard training versus curriculum learning, in standard training and curriculum learning using the CLIP method, we can get almost similar, almost equal loss value after 1,000 samples in CLIP method versus 20,000 samples in the standard training. So this is an interesting approach where, especially if you have scenario where the training time is limited, you want the model to be converged quickly, to be trained quickly, right? So you can use this CLIP method and you can train the model quickly and deploy it whenever needed. For example, in federated learning scenarios, you always need the model to be train within fixed number of time or fixed number of for each round, and you have to share the model, let's say. So this kind of applications, you can deploy the split method, and it will definitely bring some significant gains. Now, the third method, as I discussed, is knowledge distillation. So what we do is knowledge distillation. I mean, knowledge distillation is, again, it was a established technique, and most of the applications were found in classification and object detection. But crowd counting, density estimation using for crowd counting is a regression problem, right? We are actually predicting the density map. So the prediction of the density maps is we are regressing each pixel value. So it's a regression problem. So how we can utilize knowledge distillation and regression problems like crowd counting? So if you see here, we have a teacher model and we have a student model. So this is how the knowledge distillation works. So the student model actually learns from the learning of experience of the teacher model, right? And it tries to mimic the performance of the teacher model. Now, how it does it this way that when the teacher model is being trained, the teacher actually shares its outputs or its intermediate or final outputs with the student model, right? And the student model can use those outputs of the teacher model and try to, optimize its weights or its parameters in the same way to mimic the output of the teacher. Now, in terms of crowd counting or density estimation in this image, what we do is the teacher shares its intermediate outputs with the student model, and the student model takes the teacher outputs and its own intermediate outputs, and it uses a loss function to get the difference between those outputs. So this is called soft label loss, right? Soft label loss. And at the same time, as the student model, if the student model has also access to the actual or ground truth density maps, so it can also measure the loss as compared to the actual labels. And that is called the hard label loss. And at the end, it tries to optimize both. It tries to reduce both the soft label and the hard label loss, and which is called the distillation loss. So this is an online process. The teacher and student models are being trained in the same time, and the teacher model just uses the standard training process. It has the model, it has the images and the ground truth, and it is optimizing and reducing its loss value, while the student model takes its own images and the ground truth, and at the same time, it also takes the intermediate outputs from the teacher to train the model using the distillation loss, which is the composite loss of the soft level loss and the hard level loss. And using this knowledge distillation process, we tested on different data sets of different, complexities. We took actually two different teacher models. We take CSRNet and another lightweight version of CSRNet Lite. And we took three different student models, which are very shallow architecture. One is MCNN, which was proposed long before in 2016, but DrawNet and LCDNet are recent models in 2023 and actually developed by our own research group. So we took these models and we did extensive evaluation of training these models and finally like coming up with the performance benefits of knowledge distillation. We tested on these different data sets and of different complexity, different types of challenges that we discussed before. For example, weighting elimination, low light condition, scale variations, all these complexities were there in those data sets, and there was quite significant gain in the performance using knowledge distillation process. Now, I think this is the last one. So training on multimodal data. When we have multimodal data, when we have more data, we can actually train the models better. But sometimes more data cannot help. But in those cases, if you have multimodal, like for example, normally the images are RGB images, but what if there are low light conditions, for example? You need kind of other type of data which can enhance the performance, and that can be thermal images, right? So when you have RGB and thermal images both available on the same time, you can actually boost the performance of your model But the problem is thermal images are not always available. You need a thermal camera. And what if you don't have the thermal camera, right? It's not available in all cases. So in that case, we propose something that we can actually employ GAN models and in fact, a pix-to-pix GAN that we use in our study to get thermal images from RGB images alone. So we get thermal images, we actually synthesize, these synthetic thermal images from RGB images, which are real images of the scene, and using the pix-to-pix GAN. And once we have, and here is just a representation of how we can get thermal images from the actual RGB images. And when we use these different modalities like RGB and thermal images together to train this crowd model, we can see a significant boost in the performance or the counting accuracy of the model. Now, we discussed all the four techniques that we can use in here. Yeah. So what we discussed is we can boost the performance of lightweight models without increasing the complexity or the depth of the architecture. And these techniques are curriculum learning, important sampling, knowledge distillation, and multimodal data, right? We can use these models, and you saw like you can further explore these on the actual paper, like how these methods work. And here is just for the motivation purpose, we deployed a very shallow architecture that we developed here in our center, and we deployed that model to count or to get an estimation of the crowd using a single camera, and it was done on the edge devices. So we use a single NVIDIA Jetson Nano device to count or to estimate the number of people in a actually it was a metro station, and the number of people waiting outside in the queue actually for to watch a football match. So we did this real world proof of concept, and this was really a good experience, and the estimation was very accurate. And we also had an indoor scenario we want to predict the discounts, and both estimations were quite accurate using just a single Jetson Nano device and a single camera. So yeah, that's all. Thank you so much. And now, if you have any question, please feel free to ask. Otherwise, then we can jump to the next presentations.